Alright, now let's take a look at some examples to see how we really conduct the Thevenin and Norton's theorems. So example 1, find the Thevenin's and Norton's equivalent circuit across resistor 6 kilo ohm. Be very careful when you read the problem because it is telling you nothing but what is defined as part B and what is part A as the rest in the circuit. Okay, it's very, very important information as the first step. And also correspondingly, it is telling you where are the two terminals. So clearly here, this is our part B, which we cannot touch. And the rest of all circuit here are part A. And correspondingly, two terminals are here and here. Okay. Before doing anything, this is something you must be very clear. Otherwise, you're gonna go onto the wrong track. Based on those, we go ahead to follow the page 7. We have a workflow here provided. Remember to follow. So by reading here, the step A is remove part B and find open circuit voltage VOC as our Vth across those two terminals. So therefore, this is the VOC here. We should look for 6 kilo ohm as part B is removed, and we open that part across these two terminals, and then we know VOC is nothing but our Vth, because obviously to find its Thevenin equivalent circuit, we need Vth and Rth. So first of all, find Vth in this way, and then step C here, we try to find the Rth by identifying up to 3 possible cases. So our example 1 is clearly a case 1, okay, in where only independent sources presented without any dependent sources. So we go back to here, and then we gonna correspondingly zero all of the independent sources according to page 7. By zero all the independent sources, what I mean is open the independent current source and short the independent voltage source. This is the resultant circuit. And this is also the exactly same way we deal with them in previous module 3, superposition, if you recall. So once again, zero independent sources by open the independent current source and short the independent voltage source. And then the Rth is nothing but the equivalent combined resistance for this circuit. Also cross these two terminals. And in this particular circuit, it's very straightforward. Rth is just equals to the series connection between 1 kilo and 2 kilo. After finding Rth and Vth, you still need to be very clear in terms of the concept. To the given original circuit here, we know part B, part A, and the two terminals. And therefore, it's going to equivalent to Thevenin equivalent circuit in where independent voltage Vth series connected with Rth, feeding the part B, which is 6 kilo ohm. Or in terms of Norton equivalent circuit, a Norton independent current source parallel with Rth, feeding the same part B circuit, 6 kilo. And obviously, In is just equals to Vth divided by Rth, Ohm's law, and Rn equals to Rth. If all of these concepts and ideas are clear, here's the circuit for us to find the Vth. Obviously, here VOC is equals to Vth. And how to find it? And the first thing I need to emphasize is look at this voltage source 3 volts here. We know this terminal here is open. Okay. However, be very careful. It doesn't necessarily mean the 3 volts voltage source is not contributing anything. Therefore, we are not able to remove this guy at all. Okay? Open circuit only telling you there's no current flow through. Any current here? No, nothing. Because of this open circuit. However, this voltage source remaining affecting the voltage. So we can't remove this 3 volts voltage source. Then how to find this VOC voltage across these 2 terminals then? Never forget KCL, KVL, nodal or mesh. Okay? And here I'm writing KVL inside of this big loop. Obviously it's not mesh. It's just a KVL inside of a loop I selected, this big loop, because I'm trying to involve this VOC into the equation. And you can feel free to try this equation yourself and then check my solution here. And here it is. So I'm selecting a clockwise rotation direction. So first I'm coming across 3 volts because I'm assuming I'm beginning from this node and rotate clockwise, coming across negative terminal of 3 volts, so -3 here. And then positive terminal of VOC, so positive VOC. The last term inside of this loop is 1 kilo and 2 kilo series connected. So 3 kilo ohm times the current flow through them establish a voltage polarity like this. So 3K times the current flow through, I1 equals 0. And obviously I1 is another unknown I defined. 2 unknowns, 1 equation. Obviously not enough. We need to find something more. And here I'm writing KCL. I'm selecting the top node as the node to write KCL for. And how many currents involved in this KCL? First, we are seeing 1, 2, 3, 3 branches. However, we just have mentioned this branch has no current because of this open circuit. So very nice. Only 2 currents involved. One is I1, we just defined in first equation. Second is just the current source. We like it, 2 milliampere. So I1 equals to 2 milliampere, however, with opposite direction. Okay, be very careful. So I1 equals to negative 2 milli. So 2 equations, 2 unknowns. We can find both. So VOC turns out to be 9 volts. And after having VOC, which is nothing but our Vth, we can find the final Thevenin equivalent circuit, including the 6 kilo ohm. So here is the Thevenin equivalent circuit. Be very careful. This part is the so-called circuit A. This is the circuit B. We didn't touch at all. And the 2 terminals in between. To circuit A, we replace everything by series connection between Vth and Rth. 9 volts, 3 kilo. Okay. Similarly, in Norton here, circuit A, circuit B, and 2 terminals in between. And I sub n parallel with Rn. Well, Rn is simple as Rth. In is equals to Vth divided by Rth, 3 milliampere. Be very careful of the independent voltage source polarity and independent current source direction. Okay, that's all for the solution of example 1. Let me know if you have any questions. All right, let's move on to example 2 here. And similarly, we are going to find the Thevenin's and Norton's equivalent circuits across resistor 1 kilo ohm. So again, very, very important at very beginning, identify the circuit A and the B, also the corresponding 2 terminals. So clearly it is saying circuit A and circuit B. respectively, and so-called terminals are here and here. With these being said, we can move on to find Vth and Rth respectively. So to find Vth, we know we're gonna remove part B and keep these two terminals open, from where we find the open circuit voltage, which is equals to the Vth. To find Rth, we need to first of all realize this is case 1 in this procedure. So only independent sources, no dependent sources. So we can zero all of them and then find the equivalent resistance. Very straightforward. So let's see the solution here. So here we are seeing I have removed the circuit B here. I keep here open. And how to find the voltage across these two terminals. Never forget applying the KCL and KVL. One mistake students always make is thinking or expecting to come up with solution results right away, but it's not quite possible. So don't think anything else, but directly step into KCLs or KVLs. Okay? So in this circuit, since I'm seeing two independent current sources and one voltage source, so I'm thinking of KCLs might be a good choice. So I'm applying a nodal analysis by choosing two nodes up here and here. So two nodes, I call them 1 and 2 respectively, to write two KCL's equations. To node 1 here, I can see there are 4 currents involved, and 2 of them are given current source. I like them very much. So 8 milli and 2 milli with current directions going in and out respectively. The rest of the 2 currents are here and here. And feel free to define any current direction, but I'm defining the current here is downwards, the current here is towards right. Correspondingly, the KCL at node 1 is like this. So the current going into the node, which is 8 milli current itself, equals to the sum of currents leaving it, 3 of them. First one is the easiest one, 2 milliampere up here, leaving it. Second one is the current downwards here through 3 kilo ohm. So write this current in terms of node voltage. If we define the node 1 voltage as V1 and then V1 minus the ground 0 divided by 3K Ohm's law, you got the current downwards through 3K. Last current towards right is also leaving node 1, so it's equals to the V1 minus V2 divided by 6K. So this is node 1 KCL. Node 2 up here, similarly we have 3 currents involved. So one current here going into it, another current here through 2K going into it, and one current leaving it downwards. So this current has been defined and written in previous node 1 KCL. We just need to copy, and the current through 2 kilo ohm into node 2 is equals to what? If you read the circuit carefully, it's equals nothing but this 2 milli. Okay? Same current direction. And current through 6 kilo ohm is equals to the V2 minus the voltage at this node divided by 6 kilo ohm. However, what is the voltage at this node? If you read the circuit carefully, it equals nothing but 12 volts due to this voltage source here. Therefore, the current here is just equals to V2 minus 12 divided by 6 kilo. Leaving the node equals to this current plus this current, 2 milli. Okay, so 2 nodes, 2 KCLs, and we find 2 unknowns, V1 and V2, so we can find both of them. However, they are not directly related to VOC yet, so we need to find open circuit voltage here. by another at least one equation. So how to find this equation? Again, don't think of any trick. Just directly step into KVL or KCL, since we are looking for a voltage here. So KVL might be a better choice. So where to write this KVL? We select a loop. You have more than one way to choose the loop, and my choice is here, this loop, which consists of 2 kilo, VOC, 12 volts, and 6 kilo. Inside of this loop, I'm writing a KVL like this. Let me explain how I come up with this equation. Okay, so you rotate along clockwise direction. First, I come across positive, negative VOC. So positive, and then I come across here, which is negative terminal, and the positive terminal of V2. So be careful. I'm not separating considering the voltage across 6K and 12 volts. I'm summing them up as V2 and a negative V2, since we are coming across negative of V2 first. So VOC minus V2. Of course, here I'm moving V2 to the other side of the equal. So here is positive V2. Okay, and then keep rotating here. I'm coming across the voltage through 2K. 2K's voltage is introduced by 2 milliampere with this voltage polarity. So it's negative 2K times 2 milli on this side. And if you move it to here, it's a positive 2K times 2 milli. This is the KVL inside of this loop. So pretty much 3 equations and 3 unknowns. We can find the VOC, which is nothing but our Vth. 25.6 volt. Next step is to find RTH. Again, case 1, the easiest case. Only independent sources. So we zero them all out by short voltage source and ending up with this circuit. No matter what, you have to somehow come up with this correct circuit. If any trouble, just let me know. Okay, and from which we can do the combining based on the module 1 knowledge. So end up with 5.6 kilo ohm as RTH. So now we have both Vth and RTH. And the result is Thevenin equivalent circuits is just like this. Vth series connected with RTH as circuit A, feeding circuit B, which is not touchable through these 2 terminals. Okay, very clear. Equivalent Norton's circuit. So B here, terminals here, and then I sub n is equals to the Vth divided by RTH. Okay, upward direction, parallel with RTH as circuit A, or say part A, same thing. So this is the solution for example 2.